In this video, we are going to be discussing surfaces. You probably picture a surface as something like this. Intuitively, it's a topological space that locally looks like the plane. The surface in the animation has a bunch of holes, and the number of holes we call the genus of the surface. Here we see the torus, which has genus 1, and here we see the sphere that has genus 0. You have probably encountered these spaces before in many different settings, so the question we want to address in this video is what exactly is a surface? A topological surface is a two-dimensional topological manifold. That is, it's a topological space that is Hausdorff, it's second countable, and locally looks like the plane. Depending on the context, this definition can be relaxed a bit by dropping either the Hausdorffness assumption or the second countability assumption, or maybe both. But this is not something we will look at in this video. In the animation we see the two-sphere, and now we are drawing a chart around the North Pole. That is, a little neighborhood that looks like an open ball in R2. Now we depict another planar open in orange, and we see that the two opens, they overlap. Since these are simply different local parameterizations of the sphere, we see that at the overlap they must be identified in some way. Namely, we have a homeomorphism that allows us to pass from one chart to the other in the overlap. This means that we can take a more constructive approach to surfaces. Namely, if we want to produce a surface, we can take a bunch of planar opens and a bunch of homeomorphisms between the desired overlaps and use these to glue. Let us show a particular example. For instance, here in blue, we see a first planar open, U1, which is a bit weirdly shaped, but it's nonetheless a topological ball. Now in yellow, we see a second planar open, U2, and in order to glue the two of them, we fix a desired overlap that we call V1 contained in U1 and V2 contained in U2. Lastly, we pick a homeomorphism phi from V1 to V2. In the animation, we are depicting the target V2 with its usual coordinates, and then we are depicting the image of the coordinates in V1 mapped through the homeomorphism phi. What we see is that despite the fact that phi is a homeomorphism, it's in fact quite wild at the central point of the chart, namely it's taking the coordinates in V1 and making them spiral extremely aggressively. What this means is that phi is a homeomorphism, but it is not differentiable at the origin. The issue with this is that the resulting surface that is obtained by gluing the two opens has no good notion of what it means to differentiate. That is, if we consider a function f with domain U2 that is smooth, and we precompose it by phi in order to yield a function with domain V1, it will follow that that function may not be smooth anymore. The punchline to this story is that if we want to do analysis in our surfaces, then the notion of topological surface is not what we want. In order to address this, we can consider instead the following definition. A smooth surface is a two-dimensional smooth manifold. This means that it's a topological space, still Hausdorff, still second countable, but that now is obtained by gluing planar opens with diffeomorphisms. As before, we can draw a planar open U1, this is still a topological ball, and a second planar open U2. The desired overlap is already shown in the animation in green, but now we glue V1 to V2 using a diffeomorphism phi. If we take the coordinates of V2 and we pass them to V1 using the diffeomorphism, we will see that these are now distorted, but they are still smooth. It follows by the chain rule that the notion of smoothness for functions in our surface is well defined across the different charts. We can now observe that since every diffeomorphism is in particular a homeomorphism, then every smooth surface is in particular a topological surface. Therefore, a very natural question is whether some sort of converse holds. To be precise, the question is whether every topological surface is homeomorphic to some smooth surface. Furthermore, if that is the case, is that smooth surface unique up to diffeomorphism? You can think of this question as taking topological surfaces and trying to put extra structure on them. Namely, we're asking whether, given a topological surface, we can put a notion of what differentiability means in it. We will answer this question a bit later in the video, but for now, let us discuss some other ways in which you could put extra structure on a topological surface. The third definition that we will consider reads as follows. A triangulated surface is a topological surface together with a homeomorphism with a simplicial complex of dimension 2. Let me recall for you what a two-dimensional simplicial complex is. Roughly speaking, it's a cell complex that is particularly well behaved. By this, we mean that the attaching maps of the faces are particularly simple and combinatorial in nature. Namely, we identify each face with a triangle, and we require that each side of such a triangle is identified with an edge in an affine manner. In particular, this means that the attaching map of the face is piecewise linear. The other condition is technical in nature, but it's good for combinatorial purposes. It says that the overlap of any two given faces is either an edge, a vertex, or nothing at all. The example shown in the animation is the typical triangulation of the two-sphere. The example shown now is a cell structure in the two-sphere that is not a triangulation. The reason is that the two faces overlap completely along their boundary, and this contradicts the technical condition we mentioned. By construction, every triangulated surface is a topological surface. And therefore, as before, we can ask ourselves whether the converse is true. That is, does every topological surface admit a triangulation? And if so, is such a triangulation unique in some way? The answers to these questions are given by Rado's theorem, which states that indeed every topological surface has a smooth structure, and this smooth structure is unique up to diffeomorphism. And similarly, every topological surface can be triangulated, and this triangulation is unique up to combinatorial isomorphism. This means that any two triangulations of the same surface can be subdivided a bunch of times, and after subdivision they will become equivalent up to identifications. To give you a naive example showing why the smooth part of the statement may be true, you should consider the cone as a subspace of R3. Away from the central point, the cone is in fact a smooth surface, and at the singular point, we nonetheless have a local model that looks planar up to homeomorphism. It follows that the cone is in fact a topological surface, and indeed what we can do is we can flatten the cone and therefore prove that the cone is homeomorphic to the disk, which does have a very natural smooth structure. Rado's theorem is extremely useful because it allows us to use different techniques to study surfaces. Namely, by assuming that we have a smooth structure, we're able to do analysis in our surfaces, and by assuming that we can triangulate, we're able to carry out combinatorial arguments. This later perspective is what we're going to explore further in this video. A very useful remark is that the combinatorics of a triangulated surface are much simpler than the combinatorics of a general simplicial complex of dimension 2. The reason for this is that being a surface constrains how the faces are glued. Namely, we cannot glue in any affine way. We have to glue in a way that makes the neighborhoods of our points be Euclidean still. In the animation, we see a two-dimensional simplicial complex which is not a surface. Indeed, we see that it is not Euclidean along the vertices nor along the edges. To be concrete, let us formalize this claim for the central edge. We fix a point P in the interior of the edge, and we claim that no neighborhood of P is Euclidean. Indeed, every punctured neighborhood of P will retract to a certain graph G that is homotopy equivalent to the wedge of two circles, which is something that cannot happen to points in the plane. What you may prove using this type of reasoning is that in a triangulated surface, it must be the case that every edge has exactly two incident faces. A two-dimensional simplicial complex may not be a surface for other reasons. An example is shown in the animation. Namely, we see that all the edges have two incident faces, but nonetheless, the central point is clearly not Euclidean. You can try to prove for yourself that the central point has a basis of neighborhoods that are homeomorphic to the wedge of two disks. Let us explain what the consequence of this is for the combinatorics of the triangulation. Suppose that we pick one of the edges that is incident to P. Then we choose one of the two faces that is incident to both the vertex and the edge. This face connects the edge that we started with a new edge that is also incident to P. This second brown edge is incident to two faces. One of them is the red one, which we've already seen, and then there's a second face incident to it that is also incident to the point P. By walking along this second face, we will reach a third edge, now depicted in pink. In general, we will keep doing this argument, walking one face at a time, but in this case we see that if we walk one more face, in green, we will go back to the original edge. And now we see the problem. These three faces together form a disk that has P in the middle. If we were working in a surface, we would be done, because this would be a Euclidean neighborhood of P. But the problem in this simplicial complex is that we can argue in the same way with the bottom edges and form a second disk. The conclusion is that in a triangulated surface, this cannot possibly happen. That is, if we start with one edge and we walk one face at a time, we will eventually walk through every possible edge and face, and therefore we will assemble a Euclidean neighborhood of P. That is, all the edges have to be connected to one another through faces. Alright, so this second result, lemma B, brings us to the end of the video. Let us summarize a bit what we've said. We discussed three different notions of what is meant by surface. There were topological surfaces, which were the least restrictive ones, and then we discussed also smooth surfaces and triangulated surfaces, which we kinda thought as being extra data on the topological surface. It turns out that there's a theorem due to Radó that allows us to pass from one of these settings to the other. And for us, it's particularly interesting to use this theorem to work in the triangulated setting. We didn't use the triangulated setting for much just yet, but we explained that a triangulated surface is simpler than a general simplicial complex. Namely, lemmas A and B give necessary and sufficient conditions in terms of how the edges and the faces are glued for a two-dimensional simplicial complex to be a triangulated surface. In the next video, we will use triangulations to classify surfaces up to homeomorphism. At this point, you may be wondering how these ideas translate to higher dimensions. You can probably already see that the definitions themselves translate nicely. Namely, we can talk about topological manifolds in any dimension, and smooth manifolds in any dimension, and triangulated manifolds. One rather subtle point about triangulations is that in higher dimensions you have to require the triangulation to be simple locally, meaning that if you take the simplices incident to a given vertex and you glue them together, so this forms some sort of neighborhood of the vertex, then the boundary of this neighborhood must be equivalent to the standard sphere, as would be the case in the usual Euclidean space. You may observe that lemma B tells us that this is always the case in dimension 2, which is why we didn't mention this before. With these definitions at hand, it turns out that the analog of Radó's theorem is also true in dimension 3, where it was proven by Moyse in the 50s. However, this is not true anymore in higher dimensions, namely, in dimension 4 onwards, there's topological manifolds that don't have a smooth structure or a triangulated structure. In higher dimensions, there are also topological manifolds that admit many inequivalent smooth structures or triangulations. Furthermore, smoothness guarantees that the triangulation exists, but the converse is not true either. As you may imagine, there's plenty of active research about the nature of manifolds in higher dimensions. Even in dimension 3, where we have Moyse's theorem, there's still plenty to be understood. This is the end of the video, so thanks a lot for watching, and make sure you watch the next video in which we use triangulations to classify surfaces.